Hello, good evening everyone. Let us get started with the session. This is our week 3 live session for the evolutionary computation for single and multi-objective optimization NPTEL lecture. Over the last few weeks, we have discussed about what optimization is, and then we also learned about how to implement it actually in terms of binary coded genetic algorithm. We'll just have a quick recap of last week's session. Over the last week, we learned about what are some of the limitations of binary encoded genetic algorithm. A binary encoded the first one starts with in binary encoded genetic algorithm. What we essentially do is we have some individuals which we represent using binary encoding. So what is the problem with that? First problem is essentially the limitation with such type of techniques is your search space becomes discrete. What exactly is this? Is say you have a variable x that you want to encode in terms of binary numbers. So for example, x belongs to certain domain, x lower limit to x upper limit. Now what we are essentially trying to do is map this to another space of dimension 0 to 2 power L minus 1, where here L is the chromosomal length. So what essentially is happening here is you are spanning from a space of range xu minus xl to 2 power L minus 1. So this is essentially causing your, this is essentially kind of discretizing your search space. So when you have your initial domain like this, now essentially your domain is getting splitted. So this is your x lower limit, this is your x upper limit. So this interval is essentially your entire span divided by the precision length that could be acquired with the corresponding chromosomal length you have specified. So this will be your xu minus xl by 2 power L minus 1. This is what we denote by the precision. So this is one of the challenge we encounter with the binary encoding. So instead of searching over entire space, now you can only get some finite interval. Say if it is between 0 and 5 and your precision length is 0.2, then you'll essentially get 0.2, 0.4. So you won't find any solutions in between 0.1 and 0.4. That is one of the limitations with binary encoding GA. The other type of limitation is something called Hamming clips. So let's consider two individual solutions as follows: 1 0 0 0 and you have 0 1 1 1 1. So if you want to convert this to decimal numbers, the first one will be 16 and the second one will be 15. Hello, good evening. Yeah. So when we look at this Hamming clips, so essentially when you happen to see two different strings, say 16 and 15, the ones shown on the screen. So 16 and 15 differ by a unit space, but the actual when you want to convert in the binary format, you have to essentially change all the bits over here. All these bits have to be interchanged to get this particular value. Since the operations we discussed over the last couple of weeks are all about crossover and mutation, where you essentially change each bit at a time. The amount of operations that require to be done to make this happen is essentially large. So the numbers which are separated consider the same in the case of 15 versus 14, 16 versus 15. So to just increase the by one unit step, you have to make a lot of operations. So this is kind of giving out to a this is kind of your performing operations in a space which are not kind of uniform. This is one of the other limitations with the binary encoded GA. So why exactly are we facing these limitations? Essentially because the way we have chosen the encoding in kind of binary strings. We can kind of do get away with this by choosing a real encoding scheme. What exactly is real encoding is we essentially do not use the binary strings like the one we used before. So we just would represent the numbers as it is. So this is the generalized algorithm we have seen for any evolutionary computation technique. So in this particular steps, we have seen like the first step is essentially the one which involves your solution representation. The binary strings, you kind of convert your number. You kind of discretize into your domain depending on your chromosomal length, and you convert it into a binary string. Instead of doing that, we use the numbers as it is. So that is a case of a real encoded. The next step is essentially the remaining steps are almost straight. Hello? Does someone have any question? Yeah, fine. So we'll just quickly go through the previous week's lectures and then we'll start with the other techniques as well. So here in the generalized algorithm, we see these particular steps. In this, the first step, you will essentially change the binary to real encoding, and the next step in initializing random population is going to be similar. But when you come to selection, this depends only on the fitness operation, so that is also not going to change. The variation operator essentially has the crossover and mutation, which are dependent on the way you choose to encode your solutions. In crossover and mutation previously when we discussed, that essentially has some swapping among the bits, or you change the bit flip. So these are essentially operations which are done only for binary and cannot be as it is implemented in real encoding. So we have to come up with a new kind of operators for dealing with real numbers. And the remaining steps, this is again depends upon your fitness function to evaluate your offsprings, and then survivor is again the mu plus lambda set. They are also depending only on your fitness values, but they do not depend essentially on your solutions. So out of all these steps, only this particular step of variation that includes crossover and mutation has something to do with the way you represent the solution. So these are the operators we are going to discuss. Some of the other techniques we have recollected last time include the real encoded genetic algorithm, which we will be discussing. We have discussed briefly over the last week's session as well. And then we have evolutionary strategies, differential evolution, particle swarm optimization, and artificial bee colony. Today we will be going to discussing about RGA. We will see an example of how to solve an optimization problem using RGA. And then we'll also discuss about particle swarm optimization and differential evolution. So that was the example we considered previously. For now, we will just stick to some of the operators we will be using. We'll just have a recap of the operators we discussed over the last week, and then we'll take an example utilizing these operators to solve an optimization problem. So last week we discussed about how we what are the parameters that need to be taken into account while designing a crossover operator. We came to know that okay, we need to have properties similar to those of binary coded GA. The crossover operator which was used in binary coded GA versus the one we are going to use in DL encoded should have some similarities among them. What are those? Like the one we discussed. The first property is essentially the average decoded values of binary strings before and after crossover should be same. This is one of the properties we discussed previously. So let's consider two strings as shown below. When you are essentially doing crossover, you are exchanging the tails. You exchange both the tails and then you come up with this. So by essentially doing this swapping, you are not changing the overall value of the average value of the particular two offsprings combined together. So let's see how it works out. So when you convert this particular number to decimal, this is how you convert, you expand it. And then similarly the other one, when you are exchanging the numbers, so only this highlighted parts, sorry, any question? Yeah. So essentially swap these two. When you essentially swap these two, you will essentially and sum up both these equations, you will again get the same value as the final value. So just by swapping, by exchanging the tails, you will not change the average value of the population. We discussed that previously. So this is one of the property we are expecting in any of the crossover operators we are going to use at a later point of time. The second is something about the spread of the operator. So we define spread as something denoted by beta, where beta depends upon the distance between the two offsprings divided by the distance between the two parents we have considered. So just to give it a perspective, so let's understand it in this particular way. If beta value, as you can see in the formula, is absolute value of O2 minus offspring, difference between the offsprings by difference between the parents, and this can range between 0 to infinite, and we consider special case of 1. The value between 0 to 1 is when you call a contracting, and if this is in this particular scenario, the offsprings tend to fall between the parents, and it can be greater than 1. If that is the case, the offsprings tend to fall apart outside of the parents, and then you have something when it is equal to 1 is what you call a stationary. Then we discussed about a simulated binary crossover operator. So this operator essentially inherits some of the properties we discussed before, that includes the spread as well as the mean property, that the average value of the decoded value should be same as before. So you see, you get one of the offsprings by essentially using this particular formula. We will just see a graphical explanation of how to do that and how to calculate beta. Beta is again a random number which is generated using this particular formula, where ui is another random number, and eta you see over here, the eta which you see over here is a user defined parameter that kind of helps you in deciding how much spread you want in your particular beta operator. So if you slightly rearrange this formula, this is what you end up with. And this is a formula we will be using to do the hand calculation for one of the optimization problems. Now if you add both these equations, you can see that turns out to be O1 plus O2 is the sum of offsprings will be similar to the sum of parents. So this is the property we were discussing, that the average value before and after the crossover should remain the same. So now let's just understand graphically what exactly is happening in the crossover operator. So let's consider two solutions. Say one of them is P1 and the other one is P2. The first step is in identifying the midpoint between P1 and P2, the average of both the solutions, P1 and P2. You got the midpoint, that is half of P1 plus P2. And then what you essentially have to do is, you know, the distance between both of them will be half P2 minus P1. Similarly on the other end, now you have to go to either one of these sides. So let's say you pick left. So this is your total distance. Now you have to decide upon your value of beta. This is the scaling parameter that we discussed, and this is the formula for beta we discussed previously, where this particular ui is a uniform random number. You need to generate a random number from the distribution 0, 1. You have to decide upon a value of eta, and once you decide upon the value of eta, you then calculate beta. From beta you apply this particular value here. So this will be your scaling. Once you apply the scaling, you get a new point over here. This is your new point. And then we discussed about one of the mutation operators. We discussed something called a polynomial mutation operator. What we essentially do is, mutation is you take the original solution x, the given input, one input, and out of this given, you scale the entire output range by some factor delta to generate a new solution. This delta is again a random value, random number. How do we generate that? We'll just understand how this happens first in a graphical way, and then we will see how to what formula we use to calculate the delta. So you just consider the same line as before, and you consider this is the lower limit, and this is your upper limit for the particular value of x. You come up with some value of x at somewhere in between these limits. Then you essentially use this particular formula to generate the value of delta. As you can see, this also has something called a parameter eta, where this is eta is again your user defined parameter. It determines how much spread you need in your solutions. So once you decide upon the value of eta, you add that scaling parameter to x, and then you get a new value of y somewhere over here. This will be your new final value after mutation. These are not the only operators. There are other possible combinations of operators. The first one is a linear crossover operator. So just consider the same two solutions, parent solutions P1 and P2, what we essentially do is you have these should be bounded within some values XL and XU. The first step is to determine the midpoint of P1 and P2. Once you select that, the next step is essentially you in the linear crossover operator, what you're essentially trying to do is get 3 points. So one point you get at the midpoint of P1 and P2. The next point will be on the other side, on to the left of P1, and you select a third point to the right of P2. Once you get these 3 points, you use their fitnesses to decide which of these out of these 3 points you select the best 2 points. If it is a minimization, you select the minimum of these 3, or it is a maximization, you select the maximum of these. Like you select the best 2 out of these three possibilities. That will be the output of your linear crossover operator. The next one is a blend crossover operator. As we have seen in the previous case, we have just taken a given value between P1 and P2. So like once your P1 and P2 are given and the limits are given, what we have essentially done is you have considered all our equidistance, like from P1, P2, everything is scaled by a factor of 0.5. Which means all of the values within this range are given are given the equal probability, which shouldn't be the case always. So here what we do, we instead of fixing the scaling parameter 0.5, we give it in the form of a delta, which can be any value. We will see the formula for calculating delta. And then now you define a range between P1 minus delta to P2 plus delta. Depending, this alpha is a parameter that determines this particular range. Alpha is again a random number we generated. And that can actually change as you progress through your generations. That means, say, when you are during your initial stages, if your parent solutions are already far apart, then you have enough space in between to explore. So you do not need essentially a larger value of delta. But when you are approaching to one of the local optima, what might happen is P1 and P2 will come much closer. Then you essentially need a larger value of alpha to explore the search space even further. So you can kind of tune this alpha depending on your generation number. Alternatively, you can also fix a value of alpha for a given particular alpha. What we do is once you decide upon the value of alpha, you calculate this delta using the above formula, and then you have this entire range between P1 minus delta to P2 plus delta. In this out of this range, we generate a random number, and that random point will be your output of crossover operator. The simulated binary crossover operator we have discussed previously. It essentially also is the same procedure, but here about P1 and P2 we generate numbers, but here instead of following previously we have considered uniform distribution from P1 minus delta to P2 plus delta. But here what we essentially do, okay, all the points in between P1 minus delta and P2 plus delta are not equally probable. So we essentially give more weightage to consider points closer to the parent solutions. So we assume a distribution, something of this particular form, to come up with the values. But you can essentially you can also have some kind of other possibilities where it kind of extends from minus infinity to infinity. If you use a Gaussian distribution, you can as well use a Gaussian distribution with the previous P1 solution as a mean. But then it happens that for a Gaussian distribution, you have from minus infinite to infinite. Then you might actually get values crossing the bounds. If that happens, then you have to essentially kind of trim those values to the value of boundary. So if some particular value of x exceeds the XL, like it is less than XL, then you kind of make it XL. Similarly, if some value exceeds the value of upper bound, then you make it equal to upper bound. And then it's a fuzzy recombination. In this particular technique, previously we have seen simulated binary crossover operator. We have a parameter called eta c. Now in this particular operation, what we essentially try to do is make eta c equal to 1. We fix the value of eta c. So we'll just see graphically how it works. So this is my solutions, parent solutions, and these are the bounds within which the value of x lies. So it's the same distribution like the previously, but the only difference is here we consider eta equal to 1. So there won't be any power value. So this will be a linear profile, as you can see here. And this width is what will be determined by, like, has to be defined by us. till now we have discussed about operators where you give in two inputs and then you take out two outputs. But in this particular operator, unimodal normally distributed crossover, you have to take three inputs, three parents, and then you give like three or more parents, and then you take two or more solutions. How do we go about doing that? Let's consider two individuals in the search space. So let this be my search space, and let the two individuals be P1 and P2 are my parent solutions. And we consider another point as well. The first step in any of these crossover operators is that the mean should not change. So we will consider the midpoint of this as PC. Now we will consider another individual from the population. Let it be P3. What we essentially try to do is we construct a perpendicular line between this. Let's denote it by capital D. And then we have the distance between P1 and P2 denoted by small d. And then we use this particular formula where your offspring is a kind of a combination given by your midpoint plus zeta times the distance between P2 P1, and then you have given a eta 1 times P1d. Like here this is a summation. Essentially here we have considered only one parent, but you can ideally have any, like you can have 3 or 4 or 5, any number of parent solutions. Depending on the number of solutions, you take a weight value of all of them, where this zeta and eta are essentially some random numbers between the uniform random numbers between 0, 1. Using these values, you take a weight combination of these to get the new offsprings. Similar to crossover, we have other possible mutation operators. The first one is a random mutation. So in this, you consider your domain between XL and XU are your lower and upper bounds. X be your inputs given. The X is the input particular at the particular generation. X is the value given to us. So what we essentially do, you need to kind of expand it. So you have defined some parameter delta. For mutation, what we essentially do is convert X to a new value Y. How do we do that? We consider this delta, the particular region delta. Out of this region, we pick some random number again. So previously our point was X. Now we are exploring a much larger space from X minus delta by 2 to X plus delta by 2. As you can see in this particular type of mutation, your search space is kind of uniform. For any point X within the region, your search space will be X minus delta by 2 to X plus delta by 2. And all of these points will be picked at a equal probability. So like if you are kind of picking these random numbers from uniform distribution. So every point, like point here or a point here would be similar, will be picked with equal probability. This might not be always useful. Like if you are at some particular solution, what usually happens is you try to pick, when you are mutating, you want points closer to value of X at higher probability than the ones farther away. And another problem you might encounter with this particular type of mutation, as you can see, is if X is closer to one of these boundaries, then either X minus delta by 2 or X plus delta by 2 will exceed the variable bounds. Then you essentially have to trim those values. So if it exceeds lower bound, you kind of make it equal to lower bound. If it exceeds upper bound, you make it equal to the upper bound. So as we have seen previously, the problem is there you are having a uniform mutation. So now we kind of come up with some non-uniform mutation, wherein the idea is to essentially give more probability to the values which are generated closer to the previous value. So one distribution we can use is something like this, where your the weightage you give to this probability of getting these values gradually decreases as you go to the bounds. This could be one way. The main idea, the central idea here is that points closer to the value of closer to the previous value should have a higher probability than the points which are farther away from it. How do you go about doing that? So you consider some y, x is your input, you want to generate a new value y, so you add some delta to y. But delta has to be generated from some distribution which gives more weightage to the previous values. So this is the formula we are going to use. As you can see here, you kind of have to pick either one of these sides. So you don't know whether you have to increase the value of x or decrease the value of x. So first we generate a random number, depending on whether the random number is less than 0.5 or greater than 0.5, which means equally saying with 50% probability you decrease the value of x, and with 50% probability you increase the value of x, or with 50% probability you move towards the lower bound, and other way you move with 50% probability you go towards the upper bound. So as you can see in this formula, there is a parameter 1 minus r to the power a, which is the kind of weightage you are giving to pick these sides. A is given by this particular formula. As you can see here, A has some parameter called T by capital T, where T is your small t, little t is your generation number, and capital T is the maximum number of generations. So you can see as the generations proceed, you are kind of, the value inside the bracket is kind of getting reduced, which means you are kind of limiting your space. And you are also, there is another parameter to control how much weightage to give as you proceed through generations, that is through the parameter B. If you have the B value to be 0, then essentially you are not giving any weightage to A, so A will be essentially 1. Then it is not adaptive. You can kind of make it adaptive by giving a higher values of B. That could be one distribution. The other simple way to do it is you just use a normal distribution. You just use the sigma with some value of sigma. Sigma is your user, it's our parameter, we define it. So once you define it, so what we essentially do here is previously when we consider in this domain, when you have some particular value of x, we are kind of taking a uniform distribution. So here the problem you might encounter is the variable will again exceed the bounds. Then again you have to trim it to meet our demands. This is what we have discussed previously. Now we'll also go through one example. Now we will consider one simple example and we will see how to actually implement this. Let's consider this problem where you want to minimize some function f of x equal to x square within the given domain -5 less than or equal to x less than or equal to 5. So our first parameter when you start with the real encoding generic algorithm is to decide upon your population size. For the sake of example, we are considering our population size to be 8, and these are my limits. Lower limit is -5 and upper limit is 5. As we can see, the first step is to initialize your random population. How do we initialize our random population? So here I've used Excel to kind of demonstrate. You can kind of use any programming language. The first step is in we generate some random numbers. So our population size is 8. So we generate 8 random numbers. I've used rand function. Rand function essentially gives you uniform random variables in the range 0 to 1. What I essentially need is to generate initial solutions within the range lower limit to upper limit. So I want numbers between -5 less than or equal to x less than or equal to 5. What I essentially have is 0 to 1. So how do I scale this? Say you generate some random number r, you have to scale it. So this is my lower limit and this is my upper limit. How do I scale it? Is say some value x between that minus lower limit by x upper limit minus x lower limit will be equal to the similar value r over here minus lower limit is essentially 0 divided by 1. So x will be xl plus the random number you have generated into xu minus xl. So using this particular equation, we get all these values of x. So x essentially what it does is it considers the lower limit value plus the random number it has generated. The random number is essentially 0.84. 0.84. So lower limit is -5 plus the random number is 0.84 times your upper limit is 5 minus your lower limit is -5. When you evaluate this, you get some value of 3.42. You kind of repeat it for all the 8 individuals we have considered. Once you are done with this, the next step is evaluating the fitness. So what we essentially do, we take all the values of x from here and we paste these values. So now when you see here, you know that your f of x is here in this particular example, f of x is x square. So you essentially do the square of all these x and you get the fitness values. That is your next step. So you do for, you iterate over all your individuals like for 1 to 8 and then get all the fitness values. The next step is in binary tournament selection. So for this binary tournament selection, what we essentially need is only your fitness values. We are not concerned about the actual values of arguments as in x. So the first step in binary tournament selection is to pick these indices. So out of, so we have indices from 1 to 8. We need to pick two individuals at a time, but at the same time, we need to ensure that they are not repeating. In the sense, for the first round, we consider 2 rounds. For the first round, when you pick from 1 to 8, say I got a number 6. All these numbers you see over here, they should be considered without replacing. Like when you pick one number 6 out of it, the next number you pick should be from 1 to 8, excluding the 6. And then after picking 6 and 5, the next number you pick should be like 1 to 8, excluding 6 and 5. So that is how you generate this. Once you are done with it, you will be only getting, out of these two solutions, only one will be picked after, one will be selected for the after tournament selection. So you will be essentially left with only four offsprings. But our population size is 8, so we do it twice. So we again start with 1 to 8. So for here, from 1 to 8, we have chosen numbers in this particular way, and then we do it again. This could be one way of doing it. The other way of doing it is you can actually consider the original series 1 to 8. So you have numbers 1, 2, 3. Yeah.
Hello.
Yeah.
Here, see, this is 1 to 8. While selecting two for tournament selection, okay, is there any criteria considering the fx value? Suppose fx value for uh, these two participating, the difference is too large, okay. So will it affect?
No. We are considered only about the index. We consider only the index. We are not worried about fitness at this point. Fitness we'll consider in the next step. At the first step, while picking the indices, we just generate some numbers, 1 to 8, depending on your population is 1 to n, you just pick numbers. You don't worry about fitness.
Okay.
If you would
So
have considered fitness,
these are randomly selected.
yeah, these are randomly selected points. The only thing you have to ensure is when you are selecting, you should not replace it back. Like you should pick random numbers without replacing.
Because in one example, I saw.
There is another method called fitness proportionate selection.
Yeah.
Yeah,
Okay.
it is in that particular way where you actually give weightage to these fitness values, where you kind of pick the individuals depending the probability to pick an individual will be proportional to its fitness.
Okay. Yeah.
You can do it that way as well. That is another technique. But here we are kind of limiting ourselves to binary tournament selection. Yeah, that the example was also there. We can do that as well as an example. So if you consider, we'll just go through that as well. So we'll consider for this particular case. So as you see here,
one more thing, can you increase the volume from at your end?
oh, okay, 1 second. Yeah, is it better? Hello?
Hello.
Yeah, is it any better?
Slightly more because this side I don't have the headset, so I cannot increase much.
Okay, now?
So if you can increase that, yes, that's fine. Yes.
Fine?
Yeah.
Yeah. Just give me a second, I'll just hold this headset. Yeah, I think now it is fine, right? I hope now it is clear. Yeah, we'll just go through fitness proportionate as well. Now for this particular example, just to say, in fitness proportionate, what you essentially do is you have something called PI, where you calculate the probability, and then you have cumulative probability. I'm just denoting it by sigma PI. So your PI is essentially, before calculating PI, you need to know the value of sigma Fi. I'm just using just have to take sum of all these functions, and then you calculate the probability of each one, which is essentially the weight value of that. So that will be f. So you calculate the probabilities. Here you can see that this particular value of 18.6 has higher value of probability because that has more fitness value. But you can see here that when you just calculate the cumulative probability, for the first one, it will be similar to PI value. But from the next on, what you essentially do is consider both the previous values. So that equal to the previous probability plus the current probability. And you kind of do it over and over again. The only step to check that this final value is 1, which essentially means the total probability of finding all the values is 1. Now what you essentially do is you kind of select your variables based on the value of PI that you get here. So you again generate some random numbers. Say suppose for the example sake, say we'll generate some random number. See, the first number I got is 0.93. So now you go through this particular value. See, the 0.93 lies somewhere here. So what you essentially do, you pick the next solution. So in your entire domain, now if you see these particular values between 0 and 1, I am referring to these particular values of sigma pi. They are between 0 and 1. So you pick some you see 0.13 will come somewhere over here, 0.14, 0.24, 0.4 somewhere here, 0.49, 0.58 and 0.78. So these are the various values you get. So if you get something in between this, you select pick index 1. If you get some value between these two, you pick index 2. In the same way, this is your final value 0.78. So if you get some random number between these two, you actually pick the solution 8. So the number which we generated is in our particular case, we got 0.93. So we essentially pick solution 8. Say you repeat it again and again. You kind of again generate a random number. You get 0.19. So 0.19 is somewhere between these two. So like it is exceeding 2 and it is between 3. So you essentially pick the next individual as 3. And then again you generate a random number. So it is 0.22. So that is again somewhere in between these two. So again select the third one. In the same way, you kind of do it for 8 times to get 8 individuals. Sorry, if you get, we have to kind of do it for 16 times since we require 16 individuals, because after tournament selection, the number of X number of inputs are there for tournament selection, out of them only X by 2 will go to the next step. So if you want 8 solutions after the tournament selection, you essentially need 16 individuals. So this particular technique is called fitness proportionate, but if you can see here, you are kind of selecting individuals with higher fitness value. So this is only for maximization problems. If you are trying to solve a minimization problem, yeah.
This how to get this PI individual values?
PI is essentially this particular value of function f of xi divided by sigma fi. You just take a summation of all this f of x for the particular value of f of x divided by total sum. So that is kind of a relative weightage given to that particular individual. Okay.
For example, first one.
Yeah.
How did you get?
First one.
0.13698.
Yeah. You do essentially 11.717. divided by summation of all the summation of all these terms.
All this. Okay.
Summation
Fine.
of all is 85.537. So you get some value like
5.
0.136.
Okay, sir.
Okay. So like this particular technique will be for maximization. So if you are solving a like in our particular case, we are solving a minimization problem. So we have to use the duality principle to rephrase our problem. Essentially, like instead of minimizing f of x equal to small x square, if you are using for this particular technique, we have to change the function f of x to minus x square. Then it will be kind of maximizing f of x equal to minus x square. Then this particular technique can be used. Yeah.
As you told the duality principle, this is a function x square,
Yes.
and for minimum minus x square. In some reference I have seen they do 1 upon x square.
Yeah, but for my particular case, like we know that there is in my particular search domain minus 5 to 5, there is an point at which this tends to infinite, right? I mean, so depending on your domain space, you can choose. For some particular functions, it might be easier to evaluate difference, but for some, like it depends on your, if your function is to, for this simple function, it just x equal to 0, it tends to infinite, so I am choosing minus x square. There might be functions where negative might not be suitable. You can kind of go with a division, but then division is always much more costlier than just a negation. Your operation costs will increase.
Okay, thank you.
Yeah. Okay, for this particular example, we'll consider the binary tournament selection. That this is one fitness proportionate is one method, but the other method is binary tournament. So here what we do, let me just erase all this. Or let it be. So once we generate these random numbers, now we pick these solutions. So you know the seventh one is essentially this particular solution 4.1. So we kind of populate all those values here. The next step after this is essentially you performing the binary tournament selection, where you compare both the individuals and you get the best value out of this. So our objective is minimization. So when you see this first one, out of these two, the minimum is essentially this particular value. So we pick that particular value. You see here the first pick is the 2, and for the second one we essentially do the same. So 7.197 will be the minimum. So 5. You kind of repeat it again. For the third one, this is the minimum. Fourth one. So you do the same and get all as minimum values. And this is the matrix you get. So these are the new indices. I have changed the indices. These are the old indices. Old indices in the sense these are the indices for the parent, and these are just be clear. These are my parent, the index notation for the parents, and these are my output in the sense offsprings. After tournament selection, the next step after tournament selection is a crossover operator. So I will be using this particular operator here. So this is the binary simulated crossover operator. So this essentially takes two parent solutions. I am considering P1 and P2 as parent solutions. If P1 and P2 are my parent solutions, you are kind of scaling them using some parameter beta, which is again a random number generated. So how do I go about doing that? The first step is essentially again randomly picking two individuals from the pair. We'll just see one more technique to get these values. So like in the previous technique we have seen, you need to get these numbers like 1 to 8, these random number, you have to pick the random numbers without duplication. One way to pick that is essentially you generate random numbers continuously so that nothing gets repeated. The other way could be you essentially generate, you take the numbers 1 to 8 and then you shuffle them. You shuffle them, you get one sequence. You shuffle them again, you get another sequence. So that's how you can get this particular value. Like once you shuffle, this is the value you get, and again you shuffle, you might get a different thing. That could be easy way to kind of implement it. If you are using any other code, like if you are using Python or something, you can kind of use an NumPy module to just do the shuffling. The technique which I have used here is I kind of generated more number of numbers so that repetition won't happen. Now in the crossover operator, the first step is essentially picking the pairs from the previously selected individuals. So previously we got 8 individuals. Now I need to kind of select from them. So these are, so the first step is again essentially generating your random numbers. So I've generated this particular random numbers between 1 to 8. So once I have generated, I have to pick the pair. So I'm essentially taking all the first 4 in the first place and the last 4 in as second pair. Using the previous indices, so sixth one is essentially, if you see the sixth one over here is minus 2.83, so I have considered that here. Similarly, the fifth one is 3.423. So in a similar fashion, I kind of populated the entire table. So you now have these operators. As you can see, like in a crossover operator, you are essentially given 2 inputs and you get 2 outputs. So here P1 superscript of T, the P1T and P2T are your inputs, P1T plus 1 and P2T plus 1 are your outputs. And so for the crossover operator, the next step is essentially you generate some random number UI. So if you can see in this particular formula, here is your U that you need to generate. That is again a uniform random number. So once you generate a U, you calculate beta using this the above formula. So this is your U and beta is essentially here in this particular case, U is minus 0.02, which is less than 0.5. So you use the first formula. So you essentially do is 0.02 to the power 1 by eta c. I have taken as value 2. You can actually change that value 2 plus 1 and you get a value of 1.361. Similarly, for the other value, like you use 1 plus beta, you get one offspring. You do for the second case, you get the second offspring. Once you have done this, you kind of got 8 possible solutions. These are the parents. But the operation here is like you do not perform a crossover always. You perform them with certain probability that is determined by that is determined by this parameter PC, that is the crossover probability. Here I have taken that to be 0.8. So what we do next is, for each of these individuals, we again generate a random number and we see if that random number is less than 0.8, then we actually perform the crossover, otherwise not. So these particular values are after crossover, these are before crossover. So once I generate this random number, say 0.22, how will I select the new one? If this particular 0.22 is less than 0.8, then I go about selecting the new value, in the sense 1.361. If it had been lesser, I mean greater than 0.8, which didn't happen in this particular case, but if it is greater than 0.8, then I will choose the old individual. This is a step of crossover. So initially you are given, before crossover, you are given with these x values, and this is after crossover. So you can see the value of f of x here. After crossover, the next step is to go through mutation. This is a formula we used for mutation. So it's the same formula. Here your parameters are again your eta m and your pm. Pm is your mutation probability. I have considered 0.5 here. You can kind of change it. Now for this particular value, once you have given x value, so I have taken x values from here. All these x values will go to the next step. These x values will go to next step. Again, we generate some random number. In this formula, if you can see for delta bar, the first step is to generate a random number. If it is less than 0.5, you use the first case. Otherwise, you use the second case. So you calculated all the values of delta. Once you get delta, you essentially substitute in this formula to get the value of y. So you can see in this particular case, like these are after your x. So this operation essentially is done to kind of explore your search space much further. Like in the crossover operator, you're essentially trying to increase your diversity. In mutation, you are kind of trying to explore your search space. So you do not perform this operation always. As you can see, like y is equal to this particular mutation only if it is greater than, if it is less than pm. In the sense, you do it only 50% of the time. Since our mutation probability is 0.5, so what we essentially do again is generate a random number. If that particular random number is less than 0.5, then we consider the new one. Otherwise, we consider the older one. So you can kind of change this value to say 0.1, or depending upon your number of variables and your problem, sensitivity of your problem, sensitivity of your variables in your particular problem, you kind of change this, tweak these values or tune these values so that you get a better convergence. And then you calculate all this. The final operation is a survivor operator. In this particular, I have used the mu plus lambda strategy, wherein you essentially take all the populations. In the sense, these are my 8 parent solutions and these are my 8 offspring solutions. Out of all these solutions, my next step is essentially to select the best 8 of them. So what I do is essentially take all of them, all the fitness values, sort them in ascending order, take the best 8 out of them, since 8 is my population size. So that leaves me with this particular population. So you can see these are my, so if you see, these are the values initially I have started with. You can see here the mean value is 10.62 previously. That is the mean fitness value. And the best is around 0.347. After doing all the above operations, I came to a value like mean of 4.005. The best value is still remaining the same. But we know for the particular case, for our particular case, f of x equal to x square, the minimum value is 0. So once we are done with this, we again repeat this again and again. So we will just see what happens if we repeat it again. Repeating again is essentially you kind of take the values you obtained before for x and start the process again. See, you can see the value. Previously we have a value of 4.005, but now the mean fitness has changed to 0.928. So it is kind of decreased. You then repeat it again. You see it kind of decreased again as to 0.352. You do the, you kind of repeat it again and again till it is kind of converged. So here if you see now here, all the values of x are similar. It's like minus 0.589 and your mean and best values are also same. Now at this particular point, this is a kind of a situation where your population doesn't have any diversity. So your crossover operator cannot do anything. Like if there is no enough diversity in the population, whenever if I just do it again and again, then I will converge to the same thing. But we have something called mutation, which kind of tries to change these values. Let us see when mutation will kick in to help accelerate this process. So you see, mutation doesn't happen always. It only happens with 50% probability. So we need to at least run through 2 iterations to see if it does really help. See, you can see here 0.072. So the mutation has changed one of these x values. If we just had crossover operator, then we would have been stuck at the previous point. Just because of mutation, now we kind of created some diversity in the population. Now with diversity again in the population, our previous operators can work again. So again, it kind of decreased from 0.304 to 0.261. 0.162. So if you kind of repeat this again and again, eventually after some generations, you will kind of get a mean value close to 0. Like you can see here, the best value has already reached around 0.005. So if you kind of repeat this over like 10 iterations or something, it will converge to the solution. I'll just stop for a few minutes here if you have any questions in this particular algorithm or in this implementation. Yeah. Yeah, you can ask. You have some question? Mr. Rakesh, I think I cannot hear you. Yeah.
Now yes, I am unmuted.
Yeah.
This as you have shown that by changing the PM, will get better results. So how to know that now PM is to be changed?
Okay, that you can kind of see, like here I haven't plotted it, but if you happen to see these values, like how best this particular value of, sorry, my screen is not visible. Yeah. So if you kind of just have a plot, which I have not done, like this is your generation counter, T is your generation counter, and this is your fitness value. It might, if you just plot mean versus this, what you might actually see is something like this. If there are too much of oscillations, which is essentially because your mutation is kind of changing it too frequently, which might not be required in your particular domain space. So that is an indication that you have to change your PM. If this is here again, still it is decreasing. So it is not that much issue, but it might actually happen that in some cases it kind of oscillates and it never converges. Then you have to essentially decrease your PM even lower. Maybe.
And then sometimes we need to change the PC also, crossover probability.
Yeah, that you can understand from your variance of population. Essentially, if you see here, these X values, these values, there is some diversity within this population, right? There are two things, like you are aware of something called variance? Variance of a population. So when you consider a normal distribution, just giving an example, you know, there are values something like this, and this spread is essentially what you define by sigma. The sigma is your standard deviation, and the square of that is essentially what you call variance. That essentially says how your variables are distributed about the mean value. So if your population is something like this, these are some individuals in my population, how much spread is there within this population is essentially what is indicated by the variance. You can have two different populations, so consider these cases. So let's just remove this. That is case 1 versus you can still have another case like this. This is my 1 and this is my 2. 1 and 2 might have essentially the same mean. Essentially, when you take average of all these points, you might still get the same value. Like average is somewhere here. You might still get the same value, but you can see 1 is wider, it's spread across even larger space compared to 2. So this essentially has more variance compared to this one. The aim of crossover operator is essentially to kind of maintain this variance within the population. If your population has enough variance, then only your selection operator can operate.
Okay.
So if at an early number of generations, like you just see across generations how your variance is changing. If in the early parts of your generation, your population variance is kind of getting reduced, then crossover is not sufficient to ensure enough diversity is there in your population. Then you kind of increase your probability of crossover. If it so happens that your variance is too large, then you might not converge again. So something like this will happen again. So then maybe you kind of reduce both the mutation probability, crossover probability, and see how variance and fitness value change over time. Clear?
This variance will be a vector or a single value?
No, in this particular case, it is a single value. Like I have considered only one-dimensional variable, right? For our particular example. So if you have a multi-dimensional problem, then you have several variances.
Okay.
Okay. Any other doubts with respect to this particular method?
No, sir.
No? Okay, fine.
You have shown many operators, notation operators. Now,
sorry, I didn't get you. Which operator?
That mutation operator. There you have told many type of mutation operators.
Yes.
So, how to select the best one for a given application?
You have to try out each and every one. But you can vaguely say in this particular way, see if your search space is kind of having so many modalities, in the sense, if your search space is, if your function, if your domain has so many local optimos or something like that, then you kind of want a mutation operator which is kind of adaptive, in the sense, as you go through your generations, it should kind of adapt it.
Yeah.
But if you have a unimodal function, something like the one I have chosen here, f of x equal to x square, it has only one optimum. So it doesn't make much of a difference. When you have something like essentially adaptivity, in the sense, you should be able to tweak or tune your mutation operator. So which means you need to have more number of parameters to control it. You can kind of think these parameters as some controllers. So here, if in this particular operator, we have seen we have only one parameter here, eta m. That kind of helps you to tune it. So previously in one of the other operators, we have seen a mutation operator which kind of varies with generations. Like we have in the formula something like t by capital T.
Yes.
If you want even finer control, there you have two parameters. There you can get more control. It's like depends on, if you want to, if you have more number of modalities, then you want more control, then you kind of choose the one which has more parameters. But then it's like, if you increase the number of parameters, then you have to kind of tune all of them to get the actual value. If you go with a lesser number of parameters, it will be easy for you to understand what's going on. That's just a trade-off. You have to try each and every possibility.
Because we for a given problem we will be selecting one type of notation. So
That's not a
I was
necessity. You
wondering
can kind
how
of
to.
change it here and there. Like you can kind of change as you go through
Okay.
iterations. Like during the initial part, you might use a random, just a random mutation. You don't use any of the adaptivity. Like initially, what you want is to just explore the search space as much as possible because your initial solutions
Yeah.
will be spread vastly, right? So initially, you might
Hmm.
start with a random mutation that is very simple to implement also computationally. And then as you go through generations, you will go to some of these local optimas. Then you kind of choose even final like a model which has more parameters, and then depending on your generation number, you kind of change it. You can use other like you can use a mix of both these operators. That depends upon you see these plots like these convergence plots. From there you understand, okay, maybe in some
Hmm.
regions I might have to choose this operator, in some other regions you have to choose something else. You have to try out these different values.
So this non-uniform mutation you told that B is a user defined.
Yes.
So means, how to define this value?
That the B is essentially, so you're referring to that particular, one second.
Yeah, that particular type non-uniform mutation. What will the range of the B?
This particular B you're referring to, right? Here, the B
Yeah,
over on the top.
this is a non-uniform mutation. Yeah, yeah. 1 minus T
This one,
upon
right?
T
Yeah.
is equal to B. Yes. Yeah. So this
Yeah, you can
B is
start out
having
with
any
one.
range?
No range. Like B is essentially your
Okay.
exponent. So if you increase B too much, then you kind of having a nonlinear one. In the sense, so
Ah,
like it just increases the nonlinearity. So you will give more weightage to your time steps. So across one time step, your change will be too much.
okay.
Do you have to give it or not
So
depends on your problem.
so B can we can take 1 or 2 something like that.
Yes.
Okay. It will be integer value.
No, not necessarily.
Okay.
That doesn't have to be an integer. Like there is no constraint on b. So if you see over the formula, so once again, it's just an exponent. It just had to be like if you it just has to be positive in the sense if it is negative, then you are kind of decreasing your mutation as you go. But you essentially have some positive value over
Hmm.
there, so that you can kind of decrease your space as you go through generations.
Okay. Thank you.
Yeah. Okay, then we'll go to the next week of lectures. So essentially that speaks about some other type of techniques. So first one is real encoded genetic algorithm. The next one is a particle swarm optimization. Give me a second. So in this particular kind of technique, the main idea is we kind of like all these evolutionary techniques we have seen previously, we mimic the nature in the sense we kind of identify some of the patterns in nature and we kind of use those to solve our problems. In particle swarm optimization, we are kind of mimicking the behavior of bees which are searching for food. So ideally, originally this algorithm was developed for continuous nonlinear functions. As you can see, like even in the previous technique of genetic algorithm, we have never used about any information about gradient. From our classic techniques where we use the traditional techniques of finding any optimization involves finding the gradient and equating it to zero. But in these evolutionary techniques, we do not require any of this gradient information. So here there are two techniques. One is the artificial life, like two methodologies. So the first one involves the one like say some birds flocking, how they essentially each bird will follow its own route. Like there are two emergent behaviors which we will see as we go. How do we model it? What are the properties that are actually required for us to implement this particular technique? So the main idea here is this in these two lines. So each individual in your population tracks his own best as well as the best out of the swarm. So when you have a swarm of bees searching for food, every bee within the swarm knows what is his best, like his own track record versus what is the swarm's track record. So if they're searching for the food, they'll kind of know, okay, which direction to go so that they'll get food always versus which direction he should go, so that he'll get he might have his own history, his own track record, which tells him which direction to go versus the track record of the swarm as a whole. These are essentially two distinct things that we are trying to mimic in this particular algorithm. One of the advantages is this has very simple operators. It doesn't have to do any complex operators like we have done previously, like computation. It involves some complex expressions, which won't be required in this particular technique. And it doesn't have any probabilities that we have to take into account. So we'll go through all the steps through an example. We'll take an example and go through all of these. We'll consider the same problem we considered previously. It's like minimize x square between the limits -5 to 5. So here, instead of individuals, we are saying particles. Particles are essentially your bees in the swarm. So we are considering 8 bees. So the main idea here is here we have two things. One is x indicates your position of the bee at a given point of time, and v is your velocity. Velocity is kind of telling you in which direction it should go. In a sense, in your search space, which direction it should go. Again, the first step in any of the evolutionary computation technique is to initialize your population. So here my population has the bees. So again, I start with the same thing. I generate uniform random numbers, and then I use the formula to generate x equal to x lower limit plus the random number times upper limit minus lower limit. Then I kind of generate all the x values. Initially, we are kind of making velocity equal to 0, which means like initially all the bees are they're about to start. As it starts, we will see how the velocity changes, how the bee kind of tracks it. So the next step is to evaluate the fitness functions. We have we take these values of x and v, and we initialize our population. This p local I have denoted by p underscore LOC. So as you can see previously, like in this, the swarm has bees, where every bee keeps track of two things: a local best and a global best. Local best depends on his own track record. Global best depends upon the track record of the swarm as a whole. So this p log is essentially your local best for that particular particle. Initially, when we are starting the generation, the best is the current value. At the current position, what is the value of fitness function is your best local possible value. As you iterate, this value kind of changes. So after identifying the p local, the next step is to go get the global best as well. This is your global best. So you can see out of all this population, our objective is minimizing. So our minimum value is 7.021. So you get this particular value. This is your global best. Global best will be same for the entire swarm. The next step is you need to update the position. So initially you have kind of given positions to each of the bees, and each one of them has 0 velocity. Now they have to kind of start moving. So how do we update the position and velocity of the bees? This particular expression we are going to use to update the position. Here we'll go through each one of them. So this vi of t plus 1 is essentially your velocity at t plus 1, and this is your initial velocity. PIB is your local best, PGB is your global best. Xi of t is essentially your actual position at t, at a given time t. So this particular expression has three terms. The first term is called a momentum term. The second one is a cognitive, and the third one is social. We will see why exactly we have given that names. So if you can see in the first expression, the velocity at t plus 1 time is proportional to the velocity at a given time t. So if a particular bee is at a given position with a given velocity, it has some inertia with which it tries to move in the same direction. So that is this momentum component. So how much weightage it has to give to its previous position. This is a kind of a memory effect, in the sense the bee knows that it is at a given position, so it tries to continue in the same position without changing anywhere. The second thing is called a cognitive. So you can see here what we are doing is essentially trying to identify the difference between the local best and the current value of the current B position. So like the B knows previously that it was at some position where it has the best possible value of objective function. But now it is at another position with some value of objective function. So it tries to move in a direction towards its local best. So this is something called cognitive. This is kind of knowing that from your previous, based on your past experience, you know, if I go in this particular direction, I'll eventually go to some best possible value. This is called cognitive. The third one is where you know there is a global best position. PG is your global best. So the entire swarm has some best possible value. So you know you can either move in that direction. So if you have some this group of bees, they know that if they go in some direction, the entire bees will have the best possible objective function. So you can either go in that particular way. But this is determined by the swarm as a whole. So we call this the social component. Social component is essentially the component giving more weightage to all the bees within the swarm. So these factors you see like W, C1 and C2 are essentially the weightage we are giving to each one of these individual components. Like how much weightage you are giving to the previous value, how much weightage you are going to give to your track record versus how much you are going to give as a social one. And for our example sake, just to give an example, we are considering these particular values. Yeah. You have a
here, this PSO and what is the correlation? If you see means this particle has any relation with the in BGA or RGA?
Sorry, I didn't get your question. Particle has any correlation with?
It is, I think, some chromosome sort of thing, equivalent to that in BGA.
Okay, you are kind of trying to identify relation between BGA and this particular technique.
Yeah.
There your individual solution, like your individuals are chromosomes, right? Here there are bees. That's it. Bees in the sense these particles.
Particle. Okay.
Yes.
Bees are particles.
Yeah.
Okay.
Particles are bees. You can consider them as each individual in your swarm. If you have some flock of birds, and each bird will be your particle.
Okay.
Okay.
Thank you.
Okay. We'll consider these particular values of W, C1 and C2. We will see also the effect of all these parameters. Like if you can see right from the expression, if you have a much higher value of omega or W, it essentially means you are giving more weightage to your previous position. The problem that you might encounter with this approach is you might often, like if you have a very high value of W, then your Vi of t plus 1 will be highly dependent upon the value of W, and you will actually cross the bound. So like your velocity will be too high that when you give a position update, after getting the velocity update, what you essentially do is the position update. Position update is essentially you take the previous value of X and add this value of whatever velocity component you are getting. So this velocity is essentially your across 1 times your delta t is essentially 1 here. Like you are moving only for one generation. So if your momentum component is too high, then your value of Vi of t plus 1 will be too high that when you add it over to the previous position of X, the value at the next time step will exceed the bounds. One second. Yeah. So it will exceed the bound. So then you have to again do the, then it, if you kind of, if it is exceeding the bounds, then the previous methodology we used is like you kind of change it to the bound. So if you have some value of X which is less than lower bound, you kind of make it equal to lower bound. If you use the same strategy here, what would eventually happen is all the points will just go to boundaries and they will stay at the boundaries. So it's like saying whatever is the maximal space, all the bees will just form kind of a 2D circle or or some kind of a substance, depending on if your domain is a circle, then all the bees will go and will just go and fly in one circle. And like this is my entire search space, but all these bees will be just stuck at the perimeters, like all of them will just go to these perimeters, and there they will just do. But that essentially is not helping you, because what you essentially want from these bees is to search over the entire space, not just the boundaries. So W should not be too high. If you give too much importance to C1 is essentially your weightage to your cognitive or your past track record. If you're giving too much importance to that particular value, what essentially happens, you will be stuck within your own past track record. So if one of the solutions among all the possible solutions is best, like out of all the possible B's, at least one of them would have been closer to the food source. So that particular one will be closer to it, while all other will be at some local optimas. Eventually, after many generations, they will gradually come to the best one. So this kind of approach is useful when you have a multimodal function. So like when you have so many optimas. But then you can also have a unimodal functions. When you are having unimodal functions, what you essentially want is all of the B's to come to the global solution as soon as possible. Like you know that if there is some global solution, all the B's should be closer to it. So if you have a unimodal function, you should choose these values in such a way that the value of C2 is much higher compared to the other values. A higher value of C2 will kind of ensure that the velocity update is given in a direction that moves the B closer to the global best. I'm just pausing for a second. So is this clear how you choose all these three parameters? Okay, we'll just go through an example and I will just show you how by just changing the value, one of these values, how it kind of affects the boundaries that I have described here. Okay. So here you can see there are two parameters R1 and R2. These are my random numbers. Here we do not deal with probabilities, but we have random numbers. Like here we do everything with 100% certainty. Like previously we are doing crossover with only some percentage, mutation with some percentage, but here the update is always done. So the first step is you essentially generate two random numbers, R1 and R2. You use the from uniform distribution. This is xt is your previous position or the current position at time t. Initially for our generation we have zero velocity, so all the particles are starting now. Next update is essentially use the above formula for these particular values of these are my chosen values of W.75, C1 1.5 and C2 as 2. Then I get a velocity update. Once I get the velocity update, I use this particular formula to calculate the next position at t plus 1 time. So yeah.
What is the criteria of selecting W, C1 and C2?
Is the same. See like criteria in the sense, if you happen to choose one of these in the wrong way, what would happen is if you have chosen a high value of W, you might not span the entire search space because you are giving more weightage to inertia. Like you are having more inertia, so you'll be stuck in one of those places. Okay. C1 is essentially saying you are giving more weightage to your own local best, and then you are trying to improve your local best. So that kind of approach works when you are having multiple optimas. Like you have a local versus a global optima, then it's better to kind of, okay, first identify local optimas. Each bee tries to get its own best, and then overall they'll try to improve. But that approach won't work when you are having something like a unimodal function where you have only one objective, only one optima. If you have only one optima, if at least one of the bees finds that optimal, you want all of the bees to go there. So in unimodal functions, what you essentially do is to increase the value of C2. It's only the relative values of these that affect, right?
So if we know that in a complex problem where multimodal this thing, it is going to happen. There this C2, how much we can take?
C1 should be relatively higher than C2. It's the relative value that matters. Like C1 should be comparatively higher than C2 if it is a multimodal function.
In multimodal?
Yeah.
So C1 will be higher than C2.
C1 should be greater than C2. Yeah.
But value will be of this order only, 1.52 like that. I can take.
If you take higher values, what essentially happen is at every iteration you are kind of giving a much larger value of update, which essentially means you are kind of skipping too many values in between. It might lead to
Okay,
oscillations. Like if your function is too sensitive to, like if your function is flat over large regions, then you can kind of have higher values of all these parameters. If your function
But in
is,
which case I can take the C1 and C2 less than 1 also. What
yeah,
does it indicate?
you can take them less than 1 as well. That will essentially give you a lesser update to the velocity. So it's like you will take more number of iterations to converge. That's it.
Okay, it means if I have better machine, I can go for that.
Yeah, but it depends. Do you have to really go that finer? Like, do you really have to do that many
Mhm.
generations is the question. It's like our entire objective is to how can we kind of do it in computationally less expensive way.
Okay.
Clear?
Yes, thank you.
Yeah. So okay, now we have at t plus 1 time we have the new positions of all the particles and the new velocities of each one of them. The next step is again you just with these given positions and velocities you update the values. So see, it might happen like in this particular case your fitness has gradually increased than before. Okay, we will see what happens if we increase the number of generations. You kind of have to repeat it again and again. So you just take whatever you got previously as velocities and paste those values here. So you can see how this has changed. The next step is updating the local best of the previous values. Okay, this is kind of exploding. So let me just change the values to parameters. So this is the values I obtained after the update, and then I just copy these values and then update these new values and kind of repeat it again and again till you reach a convergence. You can see here how the best value has kind of came to a value of 0, like from 0 point, though the mean has increased, but the best value has kind of decreased. So you can actually tweak these values. For example, say if I kind of increase the value of W from 0.75 to a much higher value, say let me give a value of my C1, C2 or 1.5 and 2. So I'm just considering a value of 5, which will be kind of a very high value. So what we are expecting is like if you are increasing your momentum too much, the updates will be too high that your variables will exceed your bounds. See the value here, 17.821. So it kind of exceeded the bounds. So if I just try to repeat it again, like if I just carry it forward to the next step, with these fitness values as the local best, then you can see how the value has kind of exploded. See, the mean fitness has increased drastically. So it's like if you give too much value to inertia, you are kind of going to end up with this problem. So you have to kind of decide upon your value depending on this, like depending on your problem, you might have to reduce it even further, say like 0.1 or something. If you start with 0.1, let's just see what happens if you start with 0.1. You just start with 0.1, then see you kind of have still a problem here. Even with 0.1 we are having some problem. Okay. But the global optima you can see here has already reached a particular value. Since we are having a unimodal function, we can kind of increase the value of C2, say to 5 or something, to give more weightage to the global optima so that it will converge much faster. And then we again repeat it, in the sense we kind of initialize the population again and see what happens if we increase the value of C2. So these are my local best. Seems like values are again exceeding the bounds. So we would have to decrease the value of W even further. Now the values are within the range. So it's like, we know it is a unimodal function, so we kind of increase the value of C2 a little bit. And since previously the values were too high, that these function values are expanding so rapidly, so I've kind of reduced them by one order to held all these values within the reasonable limit of within our variable domain. Now you can see how the value has decreased. Now you can kind of repeat it again. We will just see what happens if we repeat it. These are my position and velocity updates I got after one iteration. So what I do is again replace them with the first step. You can see how from 7.95 it kind of reduced to 6.79 to 6.75. You kind of repeat it again and again. So now your local best are these particular values. You have to update this local best. So this particular local best will be 5.243, 1.392. Okay, we will see. We'll update the local best. So for the first two is the local best is the current function value. So we update those. For the next one is the same, but this one again we have to update. So you can see 9.38 is less than the previous value. So we update the local best. Again you can see the previous local best is 8.88. The current one is 11.829. So we don't have to update the local best. Again here it is 1.551, previous one. The current is 1.789. So we don't have to update. Same again and again. In the last step, if you can see, the previous one is 9 and the current best update is 0.273. So we kind of take that as my local best. And we update it again. You can see how the value has decreased here, like from 7.703 to 6.973. You kind of repeat it again and again till you kind of reach your convergence. In the sense, essentially, the difference between both these values will remain unchanged. Like here, the difference between the best possible values, both these values become similar. In the sense, the difference between them is within the tolerance you require. Then you kind of stop your iterations. I'll just pause for again like a couple of minutes to see if you have any other questions with this methodology.
This, excuse me?
Yeah.
For
I can
termination, this, same, here the correct value is 0.
Yeah, but ideally we don't know the correct value.
Yeah. So, in this, because if an analytical solution will give around 0.
Yes.
So, best we can accept 0.05. But for termination, this mean should be also close to best value.
Yeah, if you kind of repeat it again and again, then even mean will come within certain limit.
So that will be the termination criteria.
That will be more promising criteria. Yes.
Okay. Suppose in this particle 8, 1 to 8, it may happen sometimes. Suppose only 1 or 2 are very high value, and other are close to 0. It means so we can ignore that.
I didn't get it.
See,
You
out
are
of
saying
1 to 8, suppose only 1 or 2 they are having very high value. Rest are close to close to 0. So
okay.
that time we can also terminate
No, but
because mean
okay,
value.
but okay. Let me phrase your question in this way. So you are saying you have some particles 1 to 8. So you're essentially saying out of them, some
Yeah.
particles have already reached the solution.
Yes. Yes.
So, but how do you know what is the solution? Like here we know the solution is 0. So you are saying if out of 8, 5 particles have reached 0, I will stop. But in actual
Yes.
problems, you would not know, right, that 0 is the solution.
Yes. Yes.
So you need to have some metric. So since we do not know the solution, what we're essentially saying is even after trying to increase my number of iterations, whatever I got is not changing.
Yes.
So we are treating that as a
Yeah.
condition
Okay. Okay.
instead of each and individual values. You can kind of make it in other way, saying if the value of x, you take all the population, as you go iteration to iteration, if the values of x itself are not changing,
Yeah.
that could also happen, right? So as you said, like all
Yes.
values are 0. If you just repeat it again you'll get all as zeros because that is your optima. So your
Yeah.
condition would be like if the value of x is not changing with iterations, I can stop my iterations.
Okay.
But then
Mm-hmm.
it's like here,
Yeah.
okay, for this case
Sometimes it
I've just
happens that
yeah.
some maybe 1 or 2 members they are not coming to uh, the best value. Okay.
Yeah, so then you, instead of keeping the mean value, you can just take the best value. Best value will be the minimum of all your entire one, right? So that will anyway be at one of the
Ah,
optimal solutions. So you can kind of put a stop at that point itself. But the problem with
yeah,
the
yeah.
kind of going with the best strategy is like you might actually select one of these local optimas instead of the global optima.
Yeah, yeah.
So
Actually,
preferred you
because
just go with the
if it
mean.
is a very these variables, design variables are more than 6, then this problem is there.
Okay. Then maybe you can plot these values as a function of generation. So you can see how mean varies with generation and best varies with generation. Then you can kind of
Mm-hmm.
see the difference between both of them. If
Mm-hmm.
the best is not decreasing that much, but your mean is decreasing drastically, then you are good to go. But if it so happens that your mean and best both are not changing that much, like both are almost flat,
Yeah.
which means your population is not updating properly. Like if you consider the genetic algorithm case previously, then you might have to change your crossover parameter. In this particular approach, if that particular thing is happened, then you might have to change your values of C2, I mean C1 and C2.
Okay.
It essentially means your local updates are, you're kind of getting stuck in the local update. So you might have kept a much higher value of C2 or something like that. Then you might have to change this value a little.
Okay.
Like you have to tune these parameters so that you will get the convergence. In the sense, you get a curve something like, if you just plot this is your mean and this is your best, you get something like this. Or ideally they should converge at some point.
It looks PSO will be faster than BGA or RGA.
Faster in the sense like it takes less number of iterations to converge.
Yeah, less number of computation.
Computationally it is less expensive than the genetic algorithm.
Less expensive.
Yeah, less
But
expensive.
we
Like
don't
basically
know.
here you don't have anything, right? You just
We
have to
don't
multiply
know
few
at the
operators.
beginning. Yeah, whether generally say people say that convex function criteria.
Hmm.
I don't know what is this convex function because it is if it is a means a complex problem, then how to define the complex function?
I didn't get the question. First, I understood till the part you said like it works for convex function. After that,
Objective function,
okay,
whether
objective function.
it should be convex or concave, there's some criteria is there, no? For,
No, you can think of it this way. See, convex is like, I'm just giving an example of a 1D case. If you just take a 1D function,
ah,
you have f of x versus x. Convex function is essentially saying something like this. If you consider any point, any two different points, it's like you have some minima here. The convex function is like if you just draw a line between these 2 points, you just won't cut any other point through the curve. That is a convex function. So like if you just take 2 points on the curve and you just draw a line, it won't touch any other point on the curve. That is a convex line. I mean convex curve in 2D.
okay.
Or just to say, you can see the shape of the curve, right? I mean, simply, just to give it
Okay.
intuitive understanding, you
Here
can see
the
like, it is
here
for
the
these
here the minima
functions.
is well defined.
Here you have a minima, I mean, you have an optimal.
Yes.
If you have a function something like
Yes.
this, you don't, like, we'll just consider another example. Like if, just consider the opposite. Even this is a convex function, but still, if you want to try to find a minimum of this particular function, you would never get a minima.
Yes.
So you have to formulate your objective function in such a way you have a minima. Otherwise, there is no objective in doing all these things.
Actually, here in one or two variables, this is easy. But when I go for some design,
Yeah. Can you
so
give an
there will be
example?
more variables. Pardon?
No, I'm just asking, like, can you give an example as in which design you are
Yeah,
referring
suppose
to?
you are doing it for plant operation.
Okay.
Okay, in plant there may be 10 parameters.
Okay, your number of parameter increases.
So
Yeah.
design variables will be 10.
Hmm.
Then we don't know the shape of this function, objective function.
Yeah, but you can understand it from qualitatively, right? Just to give you an example, so if you have 10 parameters, do you have an idea, like, if you increase some of the parameters, the objective function you have chosen will decrease. But if you kind of increase some other parameters, the objective function will increase. Do you have any qualitative relationship in that particular way, which kind
Yeah,
of
yeah.
tells you that there are some competing parameters? If I can adjust, then
Yes.
if you have something like that, then you can kind of rest assured that, okay, there is some optima, right? If there are
Hmm.
competing parameters, then it means there is some trade-offs that you have to take. So there is an optima.
Okay.
But you will, like, this particular convex and all these things are for continuous functions. But okay, in practice, as you said, like, we won't have continuous functions. All of them are discontinuous, I mean, and discrete. Say if you're in a plant, you have number of equipment as some parameter, maybe number of millers or some milling machines or something like that is your parameter.
Yes,
Then
sir.
that only takes discrete values. 1, 2,
Okay.
and 3. It won't get any value in between. All these methods we discussed before cannot be used directly, because if you see here, x will get some value 1.352. That doesn't have any meaning for number of milling machine.
Hmm.
You have to change all these to kind of deal with those kind of stuff. We will see that towards the end of the course, how to deal with those kind of things.
So in such cases, PSO can be applied?
You have to tweak it in the sense your parameter here is like, here we have assumed everything to be real numbers, right?
Yeah.
So this cannot be applied directly. Maybe
Okay.
if you are fine with saying if I get 1.3, I will round it off to 1, then okay, it's fine. Like if you are kind of lenient in the sense, if you are not too strict saying, say if this is my final solution, it is not, but I'm just saying, if just assume this as my final population, and 0.667 is my final solution, you know, integer is like, you need only integers as answers, then you just say, okay, 0 is my answer.
What about this constraints? That criteria will be same as GA?
I didn't get it. Constraints for?
Constraints means handling the constraints,
Huh.
inequality and equality constraints.
Huh.
The same criteria will apply for PSO also or not?
Okay, till now in the course we didn't deal about constraints, so I have not covered it in this particular lecture, but as you said, like, constraints will come into something called the fitness or a penalty function, which will be covered in the
Yes.
upcoming lecture. So it is basically encapsulated in your objective function, like this f of x you are showing here, right? This has the
Yeah.
effect of that. This has nothing to do with whichever algorithm you are using. This is in the way you formulate your problem.
Uh-huh.
So you can kind of get away with it saying, okay, I will define a function in such a way that takes care of both the constraints and objective function.
Okay.
Like, I'll just give, this is just an example of, you might, depending on your problem, say if your objective function is x square, but your constraint is saying, like, I always want some constraint, let us say some constraint xy minus 1, I mean xy less than or equal to 1. I have some constraint like this. Just an example, sorry.
Yes.
If I have just a constraint like this, then what I will do, I will change my constraint function, I mean objective function, in such a way, like x square plus some constant times the deviation I am getting over here. So this constant is kind of telling you, like, if you violate the constraint, then your objective function will increase, and my objective is minimize the objective function. So that could be one way of dealing with it. There are other approaches, like, okay, for your plant example, you can, if it is a linear problem, you might not have to use these particular techniques. You can directly use some of the linear programming techniques.
Okay.
that is what the professor discusses in his early lectures about the no free lunch theorem.
Okay. Yeah.
I hope that is clear. There is actually one question. Okay. So that exactly says like if you are kind of dealing with some specific problems, then you have to choose specific algorithms. These are general purpose algorithms. With this, you might not get that much efficiency. Fine. Any other questions with this particular technique?
Thank you.
Okay. Then we'll go to the next part. After particle swarm optimization, the next set of lectures discusses about differential evolution. We'll just go through the example to understand how this particular technique works. So we'll consider the same problem again. Sorry, one second. These limits are -5 to 5. This again starts with all of these algorithms start with the same basic step. We initialize the random population. We are again using the same formula previously. This will be your uniform random variable, and you use the same formula to get all these values of x. Once you get some values of x, the next step is to evaluate the fitness function. So we'll just copy these values of x and calculate the fitness values. You can see here there is already one optima, but okay, we will see like there is some maximum value, like your population has some diversity within itself. Now here, how is it different from the previous algorithms we have discussed? In all the previous algorithms, we have something like, in genetic algorithm, we have something like crossover mutation to kind of explore the search space. Like the objective is in exploring the search space. How we do it is how all these techniques have evolved. In genetic algorithm, we use crossover mutation. In the particle swarm optimization, we have something called a velocity vector, position vector, which we are updating depending on the local west and the global west of each and individual particle in the swarm. Here we have something called a mutant vector and a trail vector. So in all the previous ones, it is similar to the mutant vector is similar to your crossover operation we discussed previously. So here what we do is in your population, say you have some individuals, we randomly pick 3 individuals. Say I'm picking these 3, and what we are doing is we calculate a mutant vector. Mutant vector is essentially what we do with the mutant vector is we add it to the previous solution. So if this, we'll highlight, use a different color. So this particular thing, you call this as for the particular solution you want to change, we call this the target, and you pick these 3, pick another 3, not the target one. Like you pick one target individual, say one particle that I have to change, then you select another 3 individuals from the population, and all of the 3 should be distinct. And from these 3 vectors, you generate another vector. Using these 3, you generate a third vector, that is your vi of t plus 1. Use the third vector to update the target vector. So what you so here we have vi t. So using all these 3 vectors, just remove this thing. You generate some vector called vi of t plus 1. This is your mutant vector. What you do with this mutant vector, you essentially add the mutant vector to the target vector. So you get target plus your mutant vector will give you what is called the trail vector. We will see exactly how, like this is just an intuitive understanding of how it does. So as you can see here, it's like you have one target vector and then you have to choose 3 different individuals to generate the mutant vector, which kind of gives you with one limitation on the number of individuals. Like your number should be always greater than or equal to 4 to essentially perform this particular operation. So you cannot have a population size which is less than 4. So this is one kind of not a limitation, but this is one kind of a constraint on this particular approach. Okay, we'll just see how to implement this. So here you can see we take 3 random vectors. What we essentially do to xr1 plus this particular thing. So if you just kind of see in this particular perspective, so you have xr1 and say xr2, and you have xr3. So what we are essentially doing is, so these are my vectors. So what we are doing, xr2 minus xr3, and we are kind of taking this vector over here and adding to this. Then we get a new vector this particular new vector is my VA of t plus 1. This is what we are trying to do. So this update is essentially dependent on 3 other random vectors. This is similar to the crossover operator we have discussed previously. But in the crossover operator, we just take 2 individuals and get 2 outputs. Here we are essentially taking 3 individuals and choosing upon a vector which kind of tells us how to change my current individual. So the first step is you just generate 3 random numbers. Here the parameter, there is something called f here. The difference between this is not used directly. We scale it by some factor called f. This is again a user defined parameter. Usually, like in the paper, in the original paper of differential evolution, they have used a domain of 0, 2 for this parameter. If you kind of increase the value too high, then again depends. You can observe the convergence plot to understand the effect of the value of changing f on your convergence. Depending on that, you choose which value of f will kind of give you a smoother convergence. For this particular example, we are considering a value of 0.5. So once you consider a value of 0.5, so now the first step is generating 3 random numbers. So, and these 3 random numbers should be unique. Once I generate the 3 random numbers, I select the particular individuals. So I have, for the first case, let's say I have taken 513. For this particular scenario of 513, these are the individuals. So how? So in this particular population, 5, 1, and 3. You can see like these 5 is 1.421, which is in 1.421. 1 is minus 4.785 and 3 is minus 3.181. So you do the same for all these values and then you use the above formula like Vi of t plus 1 will be xr1 plus the factor times xr2 minus xr3. Use that formula to get the value of vt1. This will be your mutant vector. Once you get this update, the next step is going to the trail vector. So trail vector here is where you use the this is something like use a crossover probability. Is like when you get an update, you add the update and you get a new value. Now whether do I have to go with the new vector or do I choose the old vector? That I will do randomly. I will here randomly in the sense we choose a probability PC. This is something called a crossover rate. We have chosen as 0.5 in this particular example. Here if you generate a random number, if it is less than the particular value of PC, then you kind of accept the mutant vector. Otherwise you choose the same value. So you can see there are 2 criteria here. One is RA less than or equal to PC, which is like saying I do this particular operation with the probability of crossover rate. The second is something like J less than or equal to R and BR of I. This R and BR of I is essentially another random number, but this is a random number in the sense of indices. So we will see how this actually works out here. So if you can see like these are my indices and these are some random numbers I have generated. I have generated with these are generated from a uniform distribution of 0 to 0, 1. The next one is RNBR is essentially a random number within the population. It is an index. So you have index from 1 to 8. You pick one of these indices. So these are my indices. The next step is you essentially get the trail vector. So if the generator random number is less than PC, so if here it is 0.957 is greater than 0.5. So you just see the second condition. If the particular value of chosen J is essentially J is your index number. This is your J. Sorry, 1 second. J is essentially a number of variables. In our particular case, it is only one variable. So we don't have to worry about this as of now. In multi-dimensional problem, when you have more number of variables, then you kind of have to treat this particular case. Okay, in this particular example, we kind of exclude it. So this particular row is of not important for this particular example because we have one dimension problem. Okay, you generate a value of u depending on how your whether it is less than or equal to 1 second. If the probability of choosing this is less than or equal to the chosen probability, So if the generated random number is less than 0.5, so if you happen to see here this particular case of 0.423, in this particular case it is less than 0.5. So for the second index we have a new value of vt plus 1 is minus 7.77. We have as you can see here, we have to if it is less than 0.7 less than or equal to pc, then we have to choose this vi t plus 1. So we have chosen minus 7.778. We do this for similarly, if you see here 0.954, this is greater than 0.5. So for the third index we have to choose the original value. For the third index, the original value is minus 3.181. So we choose the original value minus 3.181. So we do this continuously, we will get all the values of u. Then we update the functional value, we evaluate the fitness for all these values. Next operation is selection. In selection operator, here this is a bit different. Like we in previous in the genetic algorithm, the last step is essentially a survivor operator, where you use the mu plus lambda strategy. Like if you can relate, you just list down all the, you sort all the fitness values in ascending and just select the top best. If your population size is 8, you just select the top 8 of them. In this selection operator is essentially a bit greedy, in the sense you always choose the ones which are only best. In the sense, for the first index, these trail vectors, as you can see, will only be selected only if the function value is minimum. We will see that here. One second. Okay, this new vector over here is essentially equal to old vector if you just write a condition over here. I'll just write it here. If u is your new vector, you have two possibilities, or let us say the new vector is some z or something. That is my new vector. That could be either u or x. This you are choosing depending on your function value. If f of u is actually less than or equal to the original f of x, only then you choose the value of u, otherwise you choose the value of x. So these are my trail vectors. Once I have received the trail vector values, I'll compare all these values with the original vectors. So these are my original vectors and these are my trail vectors. One second. Equal to my trail vector. These are my trail vectors. Out of this x and u, how do I go about selection? I choose only the values which has the minimum value of minimum function value. So if you can see here, here both the values are equal, so it doesn't matter. When we consider the second case, you have an objective function value of 13.112 and 21.847. So the minimum value is this particular individual. So I choose this as my solution, as the offspring, in the sense the next, it will go to the next generation. So that will be minus 3.621. If you consider this particular example of 0.006 and 4.091, the minimum is, for the seventh one, the minimum will be minus 0.075. So you can see like this is my minimal solution. So this is how you get to the final value. So you can see like I started out with this particular population, I ended up with this particular one. So you can see the mean fitness is around 7.9 and that has kind of reduced to 6.816. So we'll see how this kind of reduces as we kind of repeat the same steps again and again. So these are my generation after one iteration. So I just take these values and kind of rerun it again. So you can see this kind of reduced to 4.746. So you can see from 4.746 to it kind of reduced to 3.642. So you can kind of repeat this again till your convergence. Convergence is essentially your either within the tolerance, whether your mean or best value is not changing within the given tolerance. As you can see here, in this particular differential evolution, there are not many parameters. Like you only have, sorry, give me 1 second. like the differential evaluation technique we have discussed as only one parameter PC that determines your crossover rate. So like compared to other methods, even the genetic algorithm, we need to kind of decide upon so many parameters. Like we need to decide upon the crossover probability, mutation probability, and then within the crossover operator, we need to come up with the scaling parameter beta. And for the scaling parameter beta, we need to come up with the parameter eta c. And then similarly for mutation operator, again, we need to come up with another parameter eta m. Like there are so many parameters in genetic algorithm. But if you happen to see in the particle swarm optimization, you again have three parameters. You need to decide upon how much weightage to give for the previous value, in the sense like W, C1 and C2 we discussed, like the momentum component, the cognitive component and the social component. So again there you have many parameters, but in this particular approach your number of parameters is minimal. In the sense you only have one parameter PC. So in that perspective this is kind of a very easier to understand intuitively. Like the tuning the parameters is kind of very easy in this particular approach. So it also has other difficulties in the sense when you have a little control, you have little control over the convergence of it. You have only one parameter, so you cannot control the convergence in a way you can control in genetic algorithm. Any questions with this approach? The way we went this technique? Yeah.
Yeah, while calculating the vector, it is the only magnitude of the vector that matters, or its angle also.
Here as such we do not have any angle, in the sense like, okay, for the particular case that I have chosen is one dimensional, so you don't have to worry about anything. When you are considering a multi-dimensional problem, even then it's like you update each one of the parameters separately from others. Like say if your parameters are pressure and temperature, then the update for pressure will depend only on the pressure values. It wouldn't depend upon temperature values, like as such. Like each one of the dimensions act only in that particular dimension. You won't be adding vectors from other dimensions. Like there is no concept something called a direction here. Like you see, like the vector here is essentially meaning it's a multi-dimensional one. So
yeah,
you got it right. So the direction has no physical significance here.
Okay, sir.
Okay. Any other questions? You can see
it looks very easy.
Yeah, this is very easy to implement.
But how effective it is for a given problem? Suppose when a problem we take and compare with its GA, RGA.
Yeah, all these algorithms are general purpose algorithms. So you cannot say which one of them will perform better for some particular case. Like they are expected to perform better on general cases where you cannot exploit any particular phenomena within the process. Like if there is something that you can exploit from the, say in your case of emissions or something, you know that more or less all of them will be linear. So you can kind of exploit that to kind of design an algorithm in that particular way. So these algorithms are general in the sense you cannot say which one will better perform or something beforehand. They are meant to be like that. Like the previous question you asked about the dimension, so in that particular case this particular step will be changing. You have another parameter R and BR, like this kind of ensures that at least one of them will get changed, like at least one of the variable will get changed. So you do it for each and every variable. See here uij of t plus 1 is essentially either bij of t plus 1 or xij. Here j indicates your dimension.
Okay.
So for each and every variable you do it separately. Like you do not do all at once, or you do not combine one with other, you do individually for each and every variable. Okay.
But J, you have defined J is less than or equal to RNBR.
RNBR is essentially saying if the value of, like I will do this particular one either when the probability of when the chosen random number is less than PC, or the other case when the actual chosen, like this is like saying how to give it intuitively. So you see this particular way. So when you have 3-dimensional variables, so you have 3 x1, x2, x3, you generate random numbers again here. So you will only you will either replace it when the probability is less than 0.5, Or if you randomly pick one value, and if that is actually less than the chosen value or maybe equal to that particular value, say you randomly pick an integer from 1 to 3, you get some value of 2 and you want to change the index at 1 and your probability is 0.6, you essentially don't do that.
Yes.
If you just put R is less than or equal to PC, what will happen is your probability will be only 50%. But now we are essentially saying, not only that, we are increasing the probability a little bit by saying, okay, even if the generated index is within this particular range, you do that particular operation. So by this particular way, we are kind of promoting more to kind of take the mutant vector instead of the original vector. It's like you are increasing the probability of selecting the mutant vector.
Okay, sir.
Okay. Okay, then I think the time is up. We'll conclude for today. Thank you for joining.
Thank you.